Hello, it's me, Oscar from Aero and Hydrodynamics.
Of course, the research from TU Delft you're asking about is a significant step in understanding cloud physics. Here's a more detailed look at the experiment and its implications. The study tackles a long-standing puzzle in meteorology known as the condensation-coalescence bottleneck. In simple terms, it's surprisingly difficult for tiny cloud droplets, around 10 to 20 micrometers, to grow into raindrops, about 1 to 2 millimeters. For a droplet to become rain, its volume needs to increase by a factor of about 1 million. And the process of them simply bumping into each other and merging, coalescence, is slower than what is often observed in nature. The scientists, led by researchers at the Laboratory for Aero and Hydrodynamics, built a unique, highly controlled environment called a supersaturation cloud chamber. Creating the cloud, they created a cloud of tiny, uniformly sized water droplets by carefully controlling temperature and humidity, causing water vapor to condense. Introducing sound. A powerful sound speaker was used to introduce low-frequency sound waves into the chamber. The key was to find the sweet spot for both frequency and volume. The sweet spot. They discovered the most effective range was between 50 and 100 Hz, which is a deep bass hum. The sound needed to be very loud, between 114 and 121 dB, comparable to a loud rock concert or a jet engine at a distance. The magic happens in how the sound affects the droplets. The sound waves cause the droplets to oscillate or vibrate. Due to a principle related to fluid dynamics, hydrodynamic interactions, droplets that oscillate together are drawn toward each other. Once they get close enough, they merge, forming a larger droplet. This process, repeated millions of times, dramatically speeds up the formation of larger drops that are heavy enough to fall as rain. The primary finding was that applying sound in this specific frequency and volume range significantly accelerated the coalescence process, leading to an increase in rainfall within the chamber by up to 17%. This research is important for several reasons. Improved climate models. It provides a proven physical mechanism for droplet growth that can be incorporated into weather and climate models, making them more accurate. Current models often have to make assumptions about how quickly rain forms. Acoustic rainmaking. It opens the door to novel rain enhancement technologies. Current cloud seeding involves dispersing particles like silver iodide into clouds to encourage ice crystal formation. This acoustic method offers a completely different non-chemical approach. Future potential. While still in the laboratory phase, one could imagine future applications using drones or other platforms equipped with powerful sound emitters to target specific clouds. However, scaling this up from a small chamber to the open atmosphere presents major challenges, including the immense energy required to generate such loud sounds over a large area.